The dimensions of universal gas constant are, the options given are m1 L2 T raised to minus 2 K raised to minus 1 mole raised to minus 1, m2 L1 T minus 2 K minus 1 mole minus 1, m1 L1 T raised to minus 2 K minus 1 mole minus 1, m2 L2 T raised to minus 2 K minus 1 mole minus 1. So let's look at the general equation of the gas constant. Gas constant R can be rewritten from the ideal gas equation as PV upon NT. So the P is the pressure, V volume, N is the number of moles and T is the temperature. Now the pressure can be written as force per unit area and the remaining things are kept as it is. Now what we'll look at is that the pressure can be, the force is kg meters per second square and divided by the area, so 1 upon meter square. Volume is written in meter cube, N is the number of moles and T is in Kelvin. So now this meter square is cancelled and so there's only meter. So kg can be written as M, the meter or the length, there are two, 1 meter and over here another meter, so it will become L square. Seconds is in the denominator, so T raised to minus 2, mole raised to 1 and Kelvin raised to 1. So this becomes M raised to 1, L2, T raised to minus 2, K raised to minus 1 and mole raised to minus 1. This is similar to the option number A, hence option A is the correct answer. The quantity PV upon KT, where K is the Boltzmann constant, represents, the options given are number of moles of the gas, total mass of the gas, number of molecules in the gas and density of the gas. Let's look at the relation PV upon KT. Now in this, K is the Boltzmann constant. K can be written as R upon Na, that is the Avogadro's number and the gas constant. So this expression can be written as PV, instead of PV, using the ideal gas law or the ideal gas relation, we can write PV as nRT upon the Boltzmann's constant can be replaced by R by Na and the temperature T as it is. So from this, the temperature gets cancelled and R gets cancelled. So what we are left with is N times Na. So PV upon KT can be written as N times Na. Now N is the number of moles and Na is the Avogadro's number. So Avogadro's number represents the number of molecules in each mole. So number of molecules in each mole into the number of moles gives the number of molecules in the entire gas. Hence option C is the correct answer. 1 mole of a gas at pressure 2 Pascal and temperature 27 degrees Celsius is heated till both pressure and volume are doubled. What is the temperature of the gas? The options given are 300 Kelvin, 600 Kelvin, 900 Kelvin and 1200 Kelvin. So let's use the ideal gas equation. First of all, we need to note that the pressure is 2 Pascal, which is very less. So at low pressures, gases behave as ideal gases. So even if they haven't specified as the gas being ideal, we can use the ideal equation, and that is PV equals nRT. So therefore P1 V1 upon T1 equals P2 V2 upon T2. So this is for state 1 and this is for state 2. So before heating and after heating. Now since they have given pressure is twice and volume is also doubled, so substituting these values, so we get P1 V1 upon T1 equals P2 can be written as 2 times P1 and V2 can be also written as 2 times V1 upon T2. So these get cancelled out. Therefore T2 is equals to 4 times T1. Now instead of substituting T1 as 27 degree, let us convert it into the standard MCQs system as Kelvin. So 27 degree Celsius can be written as 27 plus 273, that is equal to 300 Kelvin. So this is T1. So therefore T2 is equals to 4 times 300, that is nothing but 1200 Kelvin. Hence option D is the correct answer. Two vessels separately contain two ideal gases A and B at the same temperature. The pressure of A being twice that of B. Under such conditions, the density of A is found to be 1.5 times the density of B. The ratio of molecular weight of A and B is, the options given are half, 2 by 3, 3 by 4 and 2. Now, since it is given as an ideal gas, let us look at the ideal gas relation. PV equals nRT. Since both uh, the volume can be written as the molecular weight upon the density, so therefore P is equals to RT, considering unit mole, divided by M upon rho. So this is for this is the general equation. So let's rearrange it in terms of molecular weight. So M is equals to rho RT upon P. So in this, R is a constant. R is a constant. So what it comes out to be as, M is equals to rho T upon P. So for the gas A, MA is equals to rho A TA upon PA, and for the gas B, molecular weight of gas B would be rho B TB upon pressure of gas B. Now taking the ratios of MA by MB, MA upon MB would give rho A upon rho B, TA upon TB, and PB upon PA. So the density, ratio of the density is 1.5 times. So 1.5, since they are at the same temperature, so the ratio would be 1, and uh, the pressure is given, pressure of A is twice that of B, so the ratio is twice of B. So this comes out to be MA by MB. You get it as 3 by 4. Hence option C is the correct answer. A mole of gas occupies a volume of 100 ml at 50 mm pressure. The volume occupied by 3 moles of gas at 100 mm pressure and at the same temperature is, the options given are 50 ml, 100 ml, 150 ml and 200 ml. Since the pressure is low, let's look at the ideal gas equation. PV equals nRT. Now for the first case, the pressure is given as 50 mm. So 50 mm occupies 100 ml volume equals 1 mole of the gas and gas constant at some temperature T. This is for the first gas. Now for the second case, a 100 mm pressure is given. So 100, the volume V2 is what we have to find out. 3 moles of the second gas are used, so N becomes 3. Gas constant and at the same temperature. So equating 1 and dividing the equation 1 and 2, we get 50 into 100 upon 100 into V2 equals 1 RT upon 3 RT. Since the temperatures are same, so we don't need to worry about that and it can get cancelled. So from this we can find out the value of V2 as 150 ml. Hence option C is the correct answer. In the given figure, the VT diagram, what is the relation between the pressures P1 and P2? The options given are P2 equals P1, P2 greater than P1, P2 smaller than P1, and the last option is cannot be predicted. So in this diagram, this is a VT diagram, and in this these lines are nothing but constant pressure lines. Let's look at the ideal gas equation. PV equals nRT. Removing the constants out, therefore V by T is proportional to 1 by P. So from this relation we have come to this equation. And this graph is a graph of volume versus temperature. So therefore from this we can see that for V by T, say a point over here, so the V is this and T is this. So if you want to find out V by T, so this angle, let's say theta, so this angle theta, tan theta is equals to V by T, so the volume upon the temperature for this particular point. So similarly, for instead of V by T we can write tan theta, so 1 by P is proportional to tan theta. So as the theta increases, the value of tan also increases, or tan theta also increases. And since it is inversely proportional, as tan theta increases, the value of P will decrease. So which means that for a larger value of theta, theta 2 is greater than theta 1. So which means tan theta 2 would be greater than tan of theta 1. And since theta 2 is greater than theta 1, so P2 would be smaller than P1. Hence option C is the correct answer. 1 mole of hydrogen gas is contained in a box of volume 1 meter cube at temperature T is equal to 300 Kelvin. The gas is heated to a temperature of T is equal to 3000 Kelvin and the gas gets converted to a gas of hydrogen atoms. The final pressure would be, the condition is given that consider all the gases to be ideal. So the options given are same as the pressure initially, 2 times the pressure initially, 10 times the pressure initially, and 20 times the pressure initially. Now, when a gas of H2 molecules is heated, and since it gets converted into hydrogen atoms, that is simple H, so H2 gets converted to 2 times H. So in this, the number of molecules has basically doubled. So therefore, in the second case, later N2 becomes 2 times N1. Now using the ideal gas relation of PV equals nRT, now in this, since the volume of the container hasn't changed, so V is a constant, the universal gas constant is also a constant, therefore we can write it as P is proportional to NT. Therefore, P1 is equals to N1 T1 and P2 is equals to N2 T2. This is for the first case and the second case. So just dividing these two, so P2 upon P1 is equals to N2 T2 upon N1 T1. N2 is twice of N1 since from over here, so 2 times N1, and T2 is 3000 Kelvin. N1 is as it is and T1 is 300 Kelvin. P2 upon P1. So therefore, what we get over here is 3 times R. So P2 is equals to 2 into 10, that is 20 times P1. So P2 is 20 times the initial pressure. Hence option D is the correct answer. The density of a certain mass of a gas at standard temperature pressure is P. If the pressure of the gas is doubled and the temperature is made one-third of its initial value, the new density will be, the options given are 3P, 4.5P, 3 rho, 4.5 rho, 6 rho and 9 rho. Now, the relation for pressure with density and RMS value is P is equal to 1 by 3 rho C square, where C is the RMS value. Also, C is equals to root of 3 RT upon M. So C square can be written as 3 RT upon M. Now substituting this in this equation, so we get P is equals to 1 by 3 times rho into 3 RT upon M, that is nothing but rho RT upon M. Now rho can be, this can be reshuffled to find out, to get the value of rho as PM upon RT. Now in this relation, M and R are constants. So therefore, we can generalize it as rho is proportional to P by T. Rho is proportional to P by T. Now the condition is given that the pressure of the gas is doubled. So the new pressure P dash is 2 times initial pressure and the temperature is made one-third. So therefore T dash is equals to one-third of initial temperature T. So using this relation, we get rho 2 upon rho 1 is equals to P2 upon P1 into T1 upon T2. Okay, so now P2 is 2 times P1, or P dash is 2 times P1. So 2, and T dash upon T, or T upon T dash would be 3. So 2 into 3 is rho 2 upon rho 1. So therefore rho 2 is equals to 6 times rho 1. Hence option C is the correct answer. The RMS speed of oxygen is V at a particular temperature. If the temperature is doubled, the oxygen molecules dissociate into oxygen atoms. The RMS speed becomes, the options given are V, root 2V, 2V and 4V. Now the relation for RMS speed given as V is equals to root of 3 RT upon M, where M is the molecular mass and T is the temperature. And since this can be, R is a constant and 3 is also a constant, we can generalize this as V. Let's take, for the second case, the temperature T is doubled, so T dash is equals to 2 times T, and since the atoms or molecules, O2 molecules dissociate into 2O molecules, so therefore the molecular mass has been reduced, so therefore M dash becomes M by 2. So using these values in this relation, so VRMS or new VRMS we get as root of 3R, T can be written as 2T upon M can be written as M by 2. So this becomes root of 3R T into 4 upon M. So this 4 can be taken out of the root as 2 root of 3 RT upon M. Now this root of 3 RT upon M is nothing but the initial V that is given here. So therefore V dash RMS or new V RMS is equal to 2 times the old V RMS. Hence option C is the correct answer. If the mass of all molecules of a gas are halved and their speeds are doubled, then the ratio of initial and final pressures is, the options given are 2 is to 1, 1 is to 2, 4 is to 1 and 1 is to 4. So the relation for pressure P is given as 1 by 3 rho C square. C is the RMS value. So this rho or density can be written as mass upon volume. So this relation becomes 1 by 3 m upon v into c square. So this is for the first case. Now for the second case, when the mass is halved and the speed is doubled, so p dash would be 1 by 3 times m can be written as 2m or m by 2 since mass is halved, and v is the volume, so it stays as it is, and this ratio this RMS speed is twice or doubled, so we can write it as 2c, but since it is squared, so the whole square, so this becomes as 1 by 3 m upon 2v into 4c square. So this cancelled out as 2, so therefore p dash is equals to, this 2 can be written as 2 times 1 by 3 m upon v into c square. Now m upon 3 into this and this is the same, so therefore p dash is equals to 2 times of p. So the initial pressure and the final pressure, so the ratio of p upon p dash is 1 upon 2, hence option B is the correct answer. The RMS velocity of a gas at T degrees Celsius is double the value at 27 degrees Celsius. The temperature T of the gas in degrees Celsius is, assume that the pressure remains constant. The options given are 927 degrees Celsius, 820 degrees Celsius, 1000 degrees Celsius and 195 degrees Celsius. Now the value or the expression for RMS velocity C is equals to root of 3 m 3 RT upon m. So from this relation, the R is constant and m is constant, therefore we can generalize as C is proportional to root T. Therefore we can write C1 upon C2 is equals to root of T1 upon T2. But what we know is that in the second case C2 is twice of C1, since the velocity is doubled, so C2 is twice of C1. So we can substitute this as C1 upon 2 times C1 is equal to root of T1 is given as 27 degrees Celsius, but let's convert it into Kelvin for standardization. So plus 273 upon T2. So therefore we get 1 by 2 is equals to root of 273 plus 27, that gives 300 upon T2. So squaring both sides we get 1 by 4 is equals to 300 upon T2. So T2 is equals to 1200 Kelvin. So to convert this into degrees Celsius, we need to do 1200 minus 273. So the value we get it as 927 degrees Celsius. So therefore option A is the correct answer. A gas in an enclosure has a pressure P and the temperature T Kelvin. Another gas enclosed in a container of the same volume has a pressure 2P and the temperature T by 3 Kelvin. The ratio of number of moles per unit volume of the two gases is, the options given are 1 is to 4, 1 is to 6, 1 is to 8 and 1 is to 16. So the ideal gas equation is PV equals nRT. So the number of moles per unit volume can be written as N upon V is equals to P upon RT. So let's just, instead of N upon V, let us symbolize this as N1. So therefore N1 is equals to P1 upon R times T1. So for the second case, N2 is equals to P2 upon R times T2. However, since the pressure is doubled, so 2P1, and the temperature is made 1/3, so R times T1 upon 3. So what we get is 6 times P1 upon R times T1 and 2. So this is nothing but N1. So therefore N2 is equal to 6 times N1. Therefore N1 upon N2 is equals to 1 by 6. Hence option V is the correct answer. A vessel contains 1 mole of O2 gas, molar mass 32, at a temperature T. The pressure of the gas is P. An identical vessel containing 1 mole of helium gas, molar mass is equals to 4, at a temperature 2T, has a pressure of, the options given are P by 8, P, 2P and 8P. Now in this, let's use the ideal gas relation, PV equals nRT. So since both the masses or both the vessels contain 1 mole of each gas, so therefore the number of moles is 1, and since the volume is equal, so for 1 mole of gas at constant volume, we get the relation as P is proportional to T, and therefore P2 upon P1 is equals to T2 upon T1. Now the temperature is doubled for the second gas. So therefore P2 upon P1 is equals to 2 times T1 upon T1. So therefore P2 is equals to 2 times P1. Hence option C is the correct answer. Average kinetic energy of 3 kg of N2 gas at normal temperature and pressure is, the options given are 3 by 56 RT, 9 by 56 RT, 11 by 56 RT and 13 by 56 RT. So the formula for kinetic energy of mkg of a gas is given by 3 by 2 times RT upon the molecular mass into the weight. So that becomes 3 by 2 times RT, and for nitrogen has a atomic mass of 14, so molecular mass of N2 becomes 14 into 2, that is 28. So M is 28 times 3 kg. So this comes out to be 9 upon 56 RT. Hence option B is the correct answer. If the energy of a gas per liter is 300 joule, then its pressure will be, options given are 10 raised to 5 Newton per meter square, 2 into 10 raised to 5 Newton per meter square, 3 into 10 raised to 5 Newton per meter square, and 6 into 10 raised to 5 Newtons per meter square. Now 1 liter can be written as 1000 centimeter cube, and this centimeter cube can be converted into meter cube. So 1000 centimeter cube is nothing but 10 raised to minus 6 meter cube. So this comes as 10 raised to minus 3 meter cube. So therefore basically 1 liter is nothing but 10 raised to minus 3 meter cube. Now energy per meter cube, since energy per liter can be written as energy per meter cube, is given as 300, but since 300 is per liter, so per meter would be 10 raised to minus 3, so that is nothing but 300 into 10 raised to 3 joules. Now the formula for energy, kinetic energy, is given as 3 upon 2 PV. So energy per unit volume or energy per meter cube, that is here, is 3 upon 2 P. Since we want to find out the pressure is equals to 2 by 3 times energy per unit volume, that is 2 upon 3 into 300 into 10 raised to 3 joules. So this gets cancelled. So what we are left out is with 2 into 10 raised to 5 Newton per meter square. Joules can be written as Newtons per meter square. Hence option B is the correct answer. The average magnitude of linear momentum of a linear helium molecule in a sample of helium gas at 0 degrees Celsius is nearly the mass of the helium molecule is 6 into 10 raised to minus 27 kg and Boltzmann constant is 1.38 into 10 raised to minus 23 joule per Kelvin. The options given are 6 into 10 raised to minus 24 kg meters per second, 7 into 10 raised to minus 24 kg meters per second, 8 into 10 raised to minus 4 kg meters per second, and 9 into 10 raised to minus 24 kg meters per second. Now, the average kinetic energy average is given as half mv square, which can also be given by 3 by 2 times kBT, where kB is the Boltzmann's constant and T is the temperature. So equating these two relations, we get mv square is equals to 3 times kb into T. Multiplying both sides by m, we can get mv square is equals to 3 times kb into Tm. Now substituting the values of kb, T and m in this, we'll get 3 times kb is 1.38 into 10 raised to minus 23 and T is given as 0 degrees Celsius, so that is nothing but 273 Kelvin into the mass of the molecule, which is given as 6 into 10 raised to minus 27 kg. So 3 into 1.38 can be roughly approximated to 4, that's 273 into 6 can be approximated to 1600. 10 raised to minus 23 and 10 raised to minus 27 is a total of 10 raised to minus 50. So this is mv square, the whole square. So taking the root, we get mv is equals to root of 4 is 2, root of 1600 is 40 and root of 10 raised to minus 50 is 10 raised to minus 25. So P, the momentum P is nothing but mv, which is 2 into 4 into 10 raised to minus 24. This 40 can be written as 4 into 10 raised to minus 24. Therefore, the value of momentum P is equals to mv, which is 8 into 10 raised to minus 24 kg meter per second. Hence, option C is the correct answer. A gas at absolute temperature of 300 Kelvin has pressure of 4 into 10 raised to minus 10 Newton per meter square. Boltzmann's constant K is given as 1.38 into 10 raised to 23 joule per Kelvin. The number of molecules per centimeter cube is of the order of, the options given are 100, 10 raised to 5, 10 raised to 8 and 10 raised to 11. Now let's look at the ideal gas law. PV equals nRT. PV, instead of n, instead of R, we can multiply and divide by the Avogadro's number, R upon Na times T. Now R upon Na is nothing but Boltzmann's constant. Kb is R upon Na, whereas number of moles into Avogadro's number gives the total number of molecules. So total number of molecules N is equals to N times Na. So this relation is now modified as PV is equals to N, that is number of molecules, times R upon Na, that is Boltzmann's constant T, and Boltzmann's constant into the temperature T. So now N, that is the number of molecules per unit volume, can be given as P upon K times T. So that is, pressure is given as 4 into 10 raised to minus 10 upon K is 1.38 into 10 raised to minus 23, and T is given as 300. So this is 4 into 10 raised to minus 10 upon 4.14 into 10 raised to minus 21. So if you see the order, it comes around 10 raised to 11. So number of molecules per meter cube, since all are standard units, so per meter cube the number of molecules is 10 raised to 11. But since the question asked for per centimeter cube, so 1 meter cube is 1000 centimeter cube. So therefore, pardon me, 1 meter cube is 10 raised to 6 centimeter cube. So therefore, number of molecules per centimeter cube would be 10 raised to 6, 10 raised to 11 divided by 10 raised to 6. So that is nothing but 10 raised to 11 minus 6, it is 10 raised to 5. Hence option B is the correct answer. Total random kinetic energy of the molecules in 1 mole of a gas at a temperature of 300 Kelvin is, the value of R is given as 2 calories per mole degrees Celsius. The options given are 450 calories, 600 calories, 900 calories and 2250 calories. Now, the kinetic energy is given by 3 upon 2 kT. The K is the Boltzmann's constant, and this can be written as 3 by 2 times R upon N times T. Now, substituting the value of R, N and T as 3 upon 2, R is given as 2 calories per mole, so hence 1, and the temperature is given as 300. So this comes out to be 900 calories, hence option C is the correct answer. The ratio of specific heats Cp upon Cv equals gamma in terms of degrees of freedom, that is N, is given by, the options are 1 plus 1 by N, 1 plus N by 3, 1 plus 2 by N and 1 plus N by 2. Now, Cp minus Cv is equals to R. This is a known fact, and the value of Cv is half N times R. So therefore, Cp can be found out as R plus Cv. That is R plus, instead of Cv, we will write this half N times R. So Cp now becomes, taking out R common, so it becomes N upon 2 plus 1. Now the gamma is given as Cp upon Cv. So instead of Cp, we can write R times N by 2 plus 1 upon, and Cv is given as half of N times R. So R gets cancelled. So what we are left is 2 times N by 2 plus 1 upon N. So this can be simplified as 1 plus 2 by N. Hence option C is the correct answer. For a certain gas, gamma is equals to 1.5. Then for this gas, the options given are Cv is equal to 3R, Cp is equal to 3R, Cp equals 5R and Cv is equals to 5R. The value of gamma is nothing but Cp upon Cv. But we also know that Cp minus Cv is equals to R. So let us write Cv is equals to Cp minus R. So substituting the value of Cp over here, so we get gamma is equals to Cp upon Cp minus R. Gamma is given as 1.5, so 1.5 is equals to Cp upon Cp minus R. So 1.5 times Cp minus 1.5 times R is equals to Cp. So solving for Cp, we get 0.5 Cp is equals to 1.5 R. Therefore, Cp is equals to 1.5 upon 0.5 R. That is nothing but 3 times R. So Cp is equals to 3R. Hence, option B is the correct answer. Molar specific heat of water is C, which is equal to 74.7 joule per mole Kelvin. Its value in calories per gram Kelvin is, the options given are 2, 10, 17 and 1. Now, in order to solve this sum, we should note that 1 calorie is nothing but 4.2 joules, and therefore 1 joule is 1 upon 4.2 calories. Similarly, 1 mole of water has 18 grams. So now let's solve this. C is given as 74.7 joule per mole Kelvin. So in order to change the units, we get 74.7. 1 joule can be written as 1 upon 4.2 calories, and 1 mole is given as 18 grams. So that is, now this unit becomes calorie per gram Kelvin. So solving this value, 4.2 into 18, 4 into 18 is 74, is 72, and pardon me, 4 into 18 is 72, so 4.2 into 18 would approximately be equal to 74.7 or somewhere equal. So this value comes out to be 1 calorie per gram Kelvin. Hence, option D is the correct answer. For a gas, Cp minus Cv equals 5000 joule per kg Kelvin. If the ratio of the specific heats is 1.5, then Cp in joules per kg Kelvin is equals to, the options given are 12,000, 14,000, 15,000 and 16,000. Now, Cp minus Cv is given as 5000, whereas Cp, the ratio of specific heats, that is Cp upon Cv, is given as 1.5. Since we want to find out Cp, let us write Cv is equals to 1. Cp upon 1.5, and let us substitute this into this relation. Therefore, Cp minus, instead of Cv, let's write Cp upon 1.5 is equals to 5000. So therefore, on solving further, we get 1.5 Cp minus Cp is equals to 5000 into 1.5. So therefore 0.5 times Cp is equals to 7500, and which says Cp is equal to 7500 upon 0.5, which is nothing but 15,000 joules per kg Kelvin. Hence option C is the correct answer. The temperature of outer space has an average value of about 3 Kelvin. The root mean square speed of a proton in space is nearly, the options given are 68 meters per second, 136 meters per second, 204 meters per second and 272 meters per second. Now the value of RMS speed is given as C equals root of 3 kb T upon m. So substituting the value of kb we know as 1.38 into 10 raised to minus 23. So substituting these values, we get 3 into kb as 1.38 into 10 raised to minus 23, and the temperature is given as 3 Kelvin. upon m is given as, since it is a proton, so we know the value of mass of proton, that is standard as 1.67 into 10 raised to minus 27 kg. So on solving this, the value comes out somewhere around approximately 272.7 meters per second. Hence, option D can be as marked as the answer. Oxygen is 16 times heavier than hydrogen. Equal volumes of hydrogen and oxygen are mixed. The ratio of speed of sound in the mixture to that in hydrogen is, the options given are root of 8, root of 2 by 17, root of 1 by 8 and root of 32 by 17. Now let V be the standard volume of 1 mole. Be the standard volume of 1 mole of the gas, and if equal volumes are mixed, since equal volumes are mixed, therefore the mean density of the mixture becomes total mass upon total volume. So mean density of the mixture is nothing but total mass upon total volume, that is 32 plus 32 is the molecular weight of oxygen and 2 is the molecular weight of hydrogen upon total volume, that would be 2V. So that is 34 upon 2V, and the density of hydrogen alone can be given as 2, that is the molecular mass of hydrogen at molecule upon the volume of 1 mole. Also we need to know this formula. The dense speed of sound in a medium is given by V is equals to root of gamma times the pressure upon the density. So therefore V can be written as inversely proportional to root of the density. Therefore the velocity of sound in the mixture to the ratio of velocity of sound in hydrogen can be given as root of density in hydrogen upon density of the mixture. So that is nothing but root of 2 upon V divided by 34 upon 2V. So solving this, we get it as 2 upon 17. Hence option B is the correct answer. N molecules each of mass m by 2 of gas A and 2n molecules each of mass m of gas B are contained in the same vessel, which is maintained at a temperature T. The mean square of the velocity of molecules of B type is denoted by V square, and the mean square of the x component of velocity of A is denoted by omega square. Then omega square upon V square is, the options given are 2, root 2, 1 and 2 by 3. Now since for type A or the gas A, x component of velocity is given, therefore the total kinetic energy of gas A can be given as 3 by 2 times mass times the velocity of the x component, that is given as omega square. And similarly total kinetic energy of B can be simply given as half times mass is given as m by 2, pardon me, mass is m, this would be m by 2. So mass of the gas B is m and velocity is given as v square. So now equating these two relations, we get 3 upon 2 m omega square is equals to half m v square. So from this we get omega square upon v square is nothing but 2 by 3. So there's a correction here. 3 by 2 times m by 2. So mass of a gas is m by 2. So 3 by 2 times m by 2 into omega square would give 3 by 4 times m omega square. And solving this, we get omega square upon v square as 2 by 3. Hence, option number D is the correct answer. Air is filled at 60 degrees Celsius in a vessel of open mouth. The vessel is heated to a temperature T so that 1/4 of the part of air escapes. Assuming the volume of vessel remaining constant, the value of T is, the options given are 80 degrees Celsius, 171 degrees Celsius, 333 degrees Celsius and 444 degrees Celsius. Now for an open mouth vessel, since the vessel is given to be open mouth, so therefore the pressure is constant, and it's also given that the volume of the vessel remains constant, so V is also constant. So in this ideal gas law or ideal gas relation, PV is equal to nRT. P is constant, V is constant, R is anyways a gas constant. So therefore PV, the number of moles, can be written as mass upon molecular mass times R into T. Now in this P, V and R are constants, and the molecular mass is also constant since the gas does not change. So therefore T can be written as inversely proportional to the mass of the gas. So for T1 upon T2 is equals to M2 upon M1. T1 and T2 are the temperatures at state 1 and 2. Now after the gas is heated, 1/4 of the part, 1/4 mass escapes. So therefore M2 is equals to 3/4 of M1. So substituting the value of M2 over here, so what we get as T1 is given as 60 degrees Celsius, so 60 plus 273 upon T2 is equals to M2 is 3 upon 4 M1 divided by M1. So T2 is equals to 273 plus 60 upon 273 plus 60 into 4 upon 3, that is equals to 444 Kelvin. This T2 is in Kelvin, 444 Kelvin. So to convert into degrees Celsius, we need to subtract it by 273. So that comes out as 171 degrees Celsius. So this option B is the correct answer. Consider an ideal gas confined in an isolated closed chamber. As the gas undergoes an adiabatic expansion, the average time of collision between the molecules increases as V raised to Q, where V is the volume of the gas. The value of Q is given as ratio of specific heats gamma is given as Cp upon Cv. The options are 3 gamma plus 5 by 6, 3 gamma minus 5 by 6, gamma plus 1 by 2 and gamma minus 1 by 2. Now for this, what we need to solve is the average time of collision tau is given by mean free path lambda upon the VRMS, and this can be simplified as 1 upon root of 2 pi d square, where d is the diameter of the molecule of gas, into n upon v into root of 3 RT upon m. So this is a simplification, and in this expression the only values which are not constant is v and t. Remaining all the terms are constant. Therefore we can write tau is proportional to v upon root of t. So let this be one equation, and for the adiabatic process, since it given that it undergoes an adiabatic expansion, so for adiabatic process, t raised to t into v raised to gamma minus 1 is equals to constant. So therefore t is proportional to 1 upon v raised to gamma minus 1. So that can be written t is proportional to v raised to 1 minus gamma. Substituting the value of t as v raised to 1 minus gamma over here, we get tau is proportional to v upon root of t can be written as v raised to 1 minus gamma upon 2, and this can be simplified as tau is proportional to v raised to 1 minus 1 minus gamma upon 2. So therefore tau is proportional to v raised to gamma plus 1 upon 2, and this v raised to gamma plus 1 upon 2 is nothing but v raised to q, and hence the value of q is gamma plus 1 upon 2. Hence option C is the correct answer. The ratio Cp upon Cv is equals to gamma for a gas. Its molecular weight is m. Its specific heat capacity at constant pressure is, the options given are R upon gamma minus 1, gamma times R upon gamma minus 1, gamma times R upon m into gamma minus 1, and gamma times Rm upon gamma minus 1. Now let us solve this sum. Therefore Cp minus Cv is equals to R. This is a known relation. Let's divide by Cv. We get Cp upon Cv minus 1 is equals to R upon Cv. Cp upon Cv can be written as gamma minus 1 is equals to R upon Cv. So therefore Cv is equals to R upon gamma minus 1. Now Cp is equals to R. From this relation Cp is equals to R plus Cv. So you can write Cp is equals to R plus, instead of Cv let's write it as R upon gamma minus 1. So Cp is equals to, simplifying this relation, we get gamma times R upon gamma minus 1, and hence option B is the correct answer. The amount of heat energy required to raise the temperature of 1 gram of helium at NTP from T1 Kelvin to T2 Kelvin is, the options given are 3 by 8 Na Kb times T2 minus T1, 3 by 2 Na Kb times T2 minus 1 T1, 3 by 4 Na Kb times T2 minus T1, and 3 by 4 Na Kb times T2 upon T1. Now the amount of energy required, or the internal energy, is given by E is equals to F upon 2 nRT. Now where F is nothing but the degrees of freedom, and for helium He, the degrees of freedom F is equals to 3. Since it's a monoatomic gas, therefore F is equals to 3. So this can be written as F upon 2. The value of N can be written, N and R can be written as the number of molecules N times the Boltzmann's constant and T2 minus T1. So this is the total energy that is required to be raised. So where N is nothing but number of moles into Avogadro's number, and Kb is the Boltzmann's constant. So therefore E is equals to 3 upon 2, where putting the value of F as 3. So 3 upon 2 N times Na Kb into T2 minus T1. Now N is equals to the number of moles is equals to mass upon molecular mass. So that is nothing but 1 gram upon molecular mass is 4. So the value of E can now be written as 3 upon 2 into 1 by 4 times Na Kb T2 minus T1. So E is equals to 3 by 8 Na Kb T2 minus T1. So option A is the correct answer. A gas in an enclosure has a pressure P and temperature T Kelvin. Another gas enclosed in a container of the same volume has a pressure 2P and temperature T by 2 Kelvin. The ratio of average kinetic energy per molecule of the two gases is, the options given are 4:1, 2:1, 1:2 and 1:4. Now the average kinetic energy K is given by 3 upon 2 times Boltzmann's constant K times T. So therefore, since this is a Boltzmann's constant, so the average energy K is proportional to T. So therefore, K1 upon K2 is equals to T1 upon T2. Now T2 is given as T1 by 2, or half of T. So therefore, K1 upon K2 is equals to T upon T by 2. So therefore K1 upon K2 is equals to 2 upon 1. So therefore the option is B, 2:1.